Good morning, Jocelyn.
Good morning.
How you doing?
Tired.
Tired. All right.
But I woke up at 7, so that's a first.
Oh. Kindred spirit. She's tired. I know how that feels. All right. I'm gonna grab a couple more things.
My brother had to pull an all-nighter with his work.
That is never fun.
He was super crazy.
I don't enjoy those. I've had to do a few, and I don't like them. So. I don't like it. As always, bonk on y'all. And let me grab. I have some work to hand back.
What?
Let's see.
Why?
Work to hand back.
My friends.
It's all you guys too. Yes, ma'am.
I couldn't find the text on my
You weren't even
list and I
able to make
couldn't
it
find
to-
it.
I think it's next week for you guys. Or is that?
That's 14.
It wouldn't
I'll
let
look.
me sleep though.
I will double check.
I let
It's
you
Ethan.
sleep.
It shouldn't be there. And I didn't get it in there. And we'll make sure it doesn't get.
Like lay down and like no.
Hung up.
Drew.
Drew. And Lily. Here you go. Right, there we go. And I don't know why it's not up there. I'm gonna fuss with this thing for another second. So much fun. So did you all have a nice break?
Yes, it was nice.
I think it was. Oh, look. I think I have Jocelyn or Sky. Let's see. Somebody's ringing me. Yeah. All right, I'm trying to make sure we can get everybody in on the. There we go. Everybody at the same time. Now, is it going to be nice and connect? Why is it acting weird? Connect now.
Over break,
Yeah.
me and my sister took shovels and we started to we made a base in the huge mountain of snow that the plow guy made. And we actually had a tunnel that led and we could pop out.
Wait a minute. Hang on, Jocelyn. I had my volume down. What were you saying? Go ahead.
So our plow guy, he made a big mound of snow. So
Wow.
over break,
Okay.
me, my sister, and my friend Sam, we took shovels and we made like an actual base out of it. And we had a tunnel leading out to a hole on top.
That's amazing. We do not get enough snow for that here ever.
Oh yeah.
Ever,
We
ever.
have plenty of snow.
Well, can we borrow some for just a day? We don't want it for
Sure.
a day because nobody knows how to drive here.
That's a good point. It's like my mom, she doesn't want more snow. She's in Ohio. It just gets annoying. If you have snow time, let's see fun here, once in a while, but just no.
And over break, my dad started tapping our trees for sap.
Oh man, do you get syrup up there? Trying to get.
Because we have the proper trees for it.
You do. That's really cool.
Mhm.
All right, give me
So-
a second here. I'm trying to get
My
this.
dad has started to tap the trees.
I'll tell you how good.
That's really cool. You'll have to send us pictures or something
I know.
because we don't have a clue what that looks like.
Well, they're out right now. I can show you.
Yeah, you'll have to get us a little video or something.
Okay.
I mean, you don't have to run out of class for it, but that would be cool. All right, let me try one more time to get this to connect. It doesn't want to connect to my TV, so they can't see my screen. I don't know why. But it's being stupid.
Really fat.
Yeah. Okay, so
13.
I don't think it's going to connect to my screen for whatever reason, but that's all right. There's not a whole ton to show you. And what there is, I'll just take my tablet off and show you. So y'all had a nice break. Did anybody do anything fun or were we all kind of here?
Video games.
You played video games.
Yeah,
I don't.
I didn't
think
play
that's-
video games for half of it just because I had work.
Oh, yes.
I had to be
course.
tested computer science. I went on a weekend
vacation with my mom.
So you said, so let's see,
Oh yeah.
We had a couple- real quick, because we had a couple questions about Teacherese not doing what it was supposed to do. So y'all have, open. So many windows to go through, like button after button. So for you guys, this is my other class. All right, for you guys, you were looking for the unit test, the unit 6 test. Is that what you were looking for?
I was looking for unit 14.
No, we're unit 6. The other group was on chapter 14. Maybe you saw that.
My mom was telling me that this chapter 14 test. I'm like, I can't find a sheet for you.
Oh, it may have been, okay, maybe there was something that got crossed over. So no, you guys had a unit 6 test and that was in January on the 26th. Your unit 7 test isn't until March 9. So you guys are good. So if there was a typo somewhere or something that confused y'all, I apologize, but you didn't have a test due. So you all should be good. And then as far as today goes, we are going to do this lab today. And who have we got online? We've got, huh? It's no, it's not a hard lab. It's actually a really fun lab.
You said that last time.
Yeah.
It was fun. Last time wasn't fun.
Fun to her. You know?
It didn't work.
Well, sometimes they don't work. This one will work because I ran this the other night.
Okay.
But I wasn't thrilled with my data. I wanted more data. So what we're going to do today, so if you're online today and you're not in person, or you're absent, we are going to collect our data and get averages from the whole class. And then I'm going to put that in a lab video for you to use for your lab report. And I hope to get that out by tonight because the slides and stuff are already made. It's just a matter of me putting it all together for you so that you can use it. So yes, today your homework gets turned in, so please don't forget to turn it in. So let's have a look at our lesson, as strange as it's going to be right now, since you can't see it, but I can see it. So today we're doing acids and bases in solution, right? Right? No? All right, acids and bases in solution. So when we talk about acids and bases, do I have enough here? I think I do. I have enough where I can take, oh good, I can take my screen off. All right, I'm going to share my screen for you guys. I'm double checking a couple things here. All right, so those of you who are at home, I'm going to share so you can see my screen. I can't share it with everybody else because they can't see it, but I can hold it up. All right, so I should be able to, what did you, come on. There we go, all right, back to bed. No. Don't do that. There we go. There it goes. It just took it a minute to want to play along. All right, so anything now? It's littler than the one over there, but it still, oh well, it still works. I'm gonna hold this up here. Maybe we can prop it up. Everybody can see it. As long as my screen doesn't fall down. All right, so that's what we're today is we're going to be using some new equipment today called burettes that you guys have never used before. That's what this is called. They're super cool. Expensive. So you need to expensive. So going. So oh yeah. Yeah, they're I think they were like 120 a piece in their state. They were one of our more maybe they were less than 80 something, but still, they're 8 of them. It's a lot. So acids and bases in solution, we're going to talk about dissociation of water. Okay, so H2O, right? Okay. The thing is with water, if you leave water alone, it will actually dissociate, which means it comes apart. So when it comes apart, you can get this OH, and what do we call that? Remember? That's the hydroxide. All right, and then you can also get the H by itself, which is a hydrogen, right? What's the charge for the hydrogen? Can you see? Can you see what the charge is on it? Look, it's positive. See? So it's a positive ion. All right, and then you get this hydroxide, and what's the charge for that? It's negative. So if you have water put together, it has no charge, right? But if you want to move, if you're blinded, or do you want to put the blinds in? Drew, can you drop the blinds behind you, please? Eleanor's blinded. Thank you. So what happens is sometimes one of these free floating hydrogens will come in contact with a water molecule by itself, and it will join up. And then you'll get this little guy, H3O, and we call him hydronium. Okay, so there's lots of things that water can do completely on its own. And with an acid involved, there you go, Drew, that's good. She's good now. She can see. With an acid or a base involved, if you put them into the water, they will do the same thing. Now, acids, when there are acids present in your solution, you're going to have a lot of free floating hydrogens. And you can get a lot of hydroxides when you have bases. And a lot of bases will end in the word something something hydroxide. Today we're using sodium hydroxide in our lab, and that's our base, okay? So acids have your positive hydrogens and bases have your negative hydroxides and sometimes your hydrogen. So you have strong acids and then you have weak acids. You guys know the difference between strong acids and weak acids? Yes. What makes them strong versus weak? No. So it has to do with how much they dissociate in water. How much the acid, when it's put into an aqueous solution, breaks apart and leaves those hydrogens. Same thing with bases. It has to do with how many hydroxide, hydronium. Right? Are you there? Jocelyn, I hear your microphone, but I don't know what you're saying.
What?
I don't know. I thought I heard your microphone clipping, but I didn't know what you're saying.
Oh, no, I wasn't saying anything.
Oh, okay. All right. So a good example. We have hydrochloric acid, right? We're actually going to be using that today in our lab. And when the there's a tear. When hydrochloric acid breaks apart into the chlorine and the hydrogen. All right, and then down here, you see this free floating hydrogen, and it combines with this part and it makes this hydronium. So acids in solution, strong acids and they produce these hydronium. And then weak acids dissociate only a little. So it has to do with their chemical makeup. If it's a strong acid, it's going to break apart a lot. And you're going to get a lot of free floating hydrogens, which means you're going to get a lot of hydroniums. And if you have a weak acid, it's only going to dissociate a little. You won't get as much of these, so that you won't get as much of these. You know where you're coming from, right? Yeah. Somebody's got a mic on. Who's mic? Somebody's got a mic on. Yeah, some of it. Yeah, but if you mute it, it helps. And some of it's coming back at some of it's coming back at us, but some of it's not us. Yeah. Yeah, if y'all mute it, it's better because something's weird bouncing back. So anyway, when you have these free floating hydrogens here, these guys. So in an aqueous solution, this is what we end up with. All right. So let's go to the next. It wants me to tap here. There we go. So here's our strong bases. Same idea. And with the strong bases, what happens is you get, for example, this is sodium hydroxide. That's what we're using today. Sodium and an OH, which is your hydroxide. And when the sodium breaks off, then you get this free floating hydroxide, and he finds a random hydrogen somewhere, and they end up making water when they start to neutralize. So where does the free floating guy come from? Do we know? Remember, he came from those random water molecules that dissociated on their own. So this is always what happens in an aqueous solution. So we're always talking about in water. All right, so there were these dudes. Well, first there was this dude named Arrhenius, and he came up with a definition for what was an acid and what was a base. And it was a pretty decent definition, but it wasn't enough to explain everything. So then these dudes, Bronsted and Lowry, got together and they came up with another set of definitions, which are what we use today because they're more accurate. So a Bronsted-Lowry, you can call it Bronsted-Lowry base or Bronsted-Lowry acid, but this is kind of generally our acids and bases today, okay? And what they said is that acids donate protons. So think back to the picture we had in just a minute ago, where we had the hydrochloric acid and it broke up and we had a chlorine ion and then a hydrogen ion. And you know that hydrogen ion is positive, right? So what is it? It's a If it's positive, what kind of particle is it? It's an electron, is it a neutron, what is it? It's a proton, so, because it's positive. So acids donate the protons, that's what they do. And then the bases, what do? What's it say? They what? They accept the protons. So Bronsted-Lowry acids donate protons. It doesn't want you to,
You need a pointer.
well, I do have this, but I don't think it'll work. No. This should say protons. Anyway, they donate protons versus these guys. These guys donate protons and these guys accept protons. I'll stick it back on here and turn my whole computer around. Maybe it will be better. So that's just being strange. I can't fill in my blanks. What's the point of all my animations? Is there a glare for anybody or can you guys see? Okay, cool. There we go. Go figure. So, who drew on my screen?
Sometimes it says who does it, like
Yeah.
on.
So yeah, here we go. So your Bronsted-Lowry, look at that, boy. Stop imitating. All right, so your Bronsted-Lowry bases accept your protons and your Bronsted-Lowry acids give your protons. So let me ask you this. You guys know that acids can be super dangerous and can burn you, right? We all know that. How about bases? Can they do the same? Yep. Oh yes, bases can hurt you just as much as acids. So today what we're using in lab is actually a strong base and a strong acid, but they're very dilute. Yeah, they're very dilute. You remember last week, I think we talked last week about concentration?
That looks crazy.
Yeah. Do you remember when we talked about concentration? And then we said there was a better way to describe the concentration of an acid or base rather than saying like the volume of the solute to the volume of the solution or the volume of the solute to the solute plus the solution. Remember that whole thing? Like, is it solvent? There's so many ways to define concentration. So we use the term molarity, which is, how many moles of a certain substance are in that solution. So the stuff we're using today, our acids are going to be 0.1 molar, so a tenth of a mole. So that's pretty small. And then our bases our base is going to be 0.3 molar. So it's still they're still pretty dilute, but we're going to want to be careful with them anyway, because they can still hurt. So here's something to look at. All right, here's a graphic for you. So be sure you can see it, and let's look at it for a second. So when you look at a pH scale, what number is neutral if we're talking about acids? 7, right? Okay, and then acids and bases, 7 is neutral, means it doesn't have a whole, it's not going to go either way pH wise. So what is the number for acids? What's the high end for acids? Do you remember what the number is for the high end? Really strong? The 0. It's down here's the 1, 0. So 0 is acids, and then bases is 14. All right, but this is pH. Now remember, we just talked a minute ago about the H being associated with acids, right? The hydrogen goes with the acid. What with the bases? The OH. Remember, H goes with acid, OH goes with base. So there's also POH. We don't usually use POH, we just kind of stick with pH most of the time. But POH, if pH is talking about how many acids are there, and you've got 0 on your high end and 14 on your low end for your acid strength, then what do you think the pH scale would be? How do you think it would relate?
Higher.
It's total opposite. It's completely inverse. Because if you have, look at it this way, here's your pH, and if you have a lot of pH, if your pH is really low, it means you have a lot of these hydrogens, right? And then if you have a really low amount of hydrogens, you're going to have a really high amount of hydroxide. So it's exactly opposite. They're completely flip-flopped, the numbers.
Negate each other when it's neutral?
Yes, they do. They negate each other when it's neutral. So this is what the math actually looks like. I know that's frightening, right? So this, here's your H and your OH, and then here's your POH and your pH. And there's math that goes with this that you can do all kinds of equations to work it out that you guys don't have to do. But if you get into a higher level chemistry, you may end up learning that. And it's kind of neat because they're totally inverse. They're complete opposites. So when one does one thing, the other does the opposite. So your hydrogen concentration is your pH, and your concentration of hydroxide is your OH. So if you can always remember that the H goes with the hydrogen, it goes with the acid, The OH goes with hydroxide and it goes with the base. That's the big thing for you guys. So H goes with what?
H goes with the acid.
Acid, because it's how many hydrogen. And then OH goes with bases because it's how many hydroxide. Gosh, God, need some coffee this morning. Try it again. The H goes with what? Acids, because it's hydrogen concentration. And then the OH goes with bases because it's hydroxide. That's the big thing for you guys, really the big thing. All right, so what does pH mean? So I put this in here because it's a story. There's supposed to be a pi symbol in here, and I don't know why it disappeared. You know the symbol pi stands for 3.14?
I don't think that does not.
Yeah, it stands for 3.142, blah, blah, blah. Yeah.
Five
So
different
I asked a
colors.
question once when I was in junior high in my 7th grade pre-algebra class. I asked the student teacher named Ms. Pris Porowski what pi was. And she said it's 3.14. And I said, no, but what is it? She said, well, it's 3.1427 whatever, and gave me a couple more numbers. And I was like, no, but what is it? Like, where did it come from? And I was honestly just asking her question. And as I said right here, it ended up reducing my pre-algebra student teacher, Ms. Pris Borowski, to slobbering tears, and I felt like dirt. Because she just cried and cried because she couldn't answer my question. And she was, and I didn't mean to. I mean, I'm the last person who wants to make anybody feel bad. So she cried and slobbered tears, and it was awful because I just wanted to know. You can't just throw a number at me and tell me this works. How does it work? I want to know what it is. So what is pH? So I want to tell you guys what pH is. So this guy right here, by the way, this is S.P.L. Sorensen, and he's the guy who invented the pH scale. So the exact meaning of the P in pH is disputed, as Sorensen did not explain why he used it. He described a way of measuring it as potential differences, so that's a P. But it represents a negative power of 10 in the concentration of ions. Okay, so there's some math involved. So there's a power in there. So far we've got potential and power, right? But all those words start with P in French, German, and Danish, and those are all languages that he spoke, French, German, and Danish. So maybe he was using those. And he published in those languages too. So we know he was fluent in them. And he worked in this place called Carlsberg Laboratory, and it was French speaking, the laboratory was. And German was the dominant language for science publishing, and he was Danish himself. So it says here that he also used Q in much the same way elsewhere in the same paper when he was writing about all of this. So the P could stand for the French puissance, or the German potence, or the Danish potens, which all mean power, or it could mean potential, or he might just have labeled the test solution P. It was just solution P. That's where we got the P from. And it could be a reference to Q, because sometimes those letters, because they look like mirror images, are paired with each other in a lab. If you're labeling samples, you might label one P and one Q, because they look like they go together, even though they don't really go together. It's like a way of saying they're a pair, but not really a pair. And so there's little to support the suggestion that pH stands for Honda's hydrogeni, which means quantity of hydrogen, because some people like to say that, or potentia hydrogeni, which is power of hydrogen. So currently in chemistry, the P stands for, get this, decimal co-algorithm of, because if you're doing the math, you use decimal co-algorithm of, where you would put the letter P if you were translating the equation into English, right? And it's also used in the term pKa, which we'll get to much later, and for the acid dissociation constant, which is POH. So we don't really know what the P means. It's like the 3.14. They actually do know why that is a thing, but my teacher could not explain it to me, and she cried.
In applications, I believe they use 3.1415 instead of 3.14.
Yeah, it usually is. Yeah, I think if you round the next one up, yeah.
Why should she cry over that?
I don't know. Well, let me tell you what. So there were two other boys in my class. Yeah, okay. Edwin and Mike were two boys in my class, and they picked on her a lot. And I've since teased Mike because he's a minister now, and I'm like, you remember that student teacher you made cry all the time, Mike? Because you were now he's a minister. But they'd be like, yo, Miss Pris. And they'd ask her some question, and poor Miss Pris Borowski would try and come up with the answer. They tried to stump her because that was kind of their shtick. So I think she was already like fragile. And then I asked her a question she couldn't answer, and she felt that. So neutralization. What's neutralization? What happens when an acid and base come together? You guys know?
Maybe.
No, make it big.
No.
No, when an acid and base come together, they neutralize. So what's that mean? That means the hydroxide, the OH from the base, and the hydrogen from the acid come together and you get H2O, right? Yes, Drew.
You get water and salt.
Yep, you get a water and a salt. Well, here's the water. So the salt is what we call it's your conjugate. So say you have, like today you're doing sodium hydroxide. Let me see, I'll write it here. I'll put on my annotate. I'm going to show you guys. So say you have, where'd it go? Stop. Here it is. Say you have, let me write it in white so you can see it. Like we're using today, we have an HCl plus NaOH. Okay, you guys see that? Where is the H for the acid? Which one of these is the acid? The HCl or the NaOH?
Where was the acid?
Which one of those is the acid?
HCl.
Yeah, HCl, because it has the H, right? And which one is the base?
NaOH.
The NaOH, right, because there's your OH, right? So when these two guys get together, the chemical reaction that you get is you get this H2O, right? This is this right here. There's your OH and your H, and you get H2O. And then what's left over? The salt, NaCl. So when an acid and base get together, you always have water and a salt that it's always produced. Now your salts, what they call these conjugate pairs, and we'll get to that. But you're always going to get this. When you put an acid and base together and they neutralize, you're going to lose the hydrogen and the hydroxide that are parts of other components. They're going to come together and make water. And then what should your pH be at this point? If it's completely neutralized. 7, yeah, if it's completely neutralized. Now, the thing is, it doesn't always completely neutralize because sometimes you're going to have more acid than you have base. And in those cases, it won't completely neutralize, right? But if you have equal amounts, then you'll completely neutralize and you'll get water and salts every single time. It's just the way it works. Okay, go away, annotate. Oh gosh, let's do that thing. Clear. Go away. There we go. So then when acid and base are mixed, hydrogen ion and the base combines with the hydroxide ion and the base combines with the hydrogen ion from the acid and they form water and salt, and that's neutralization. So B plus A, here's your B, here's your A, you get B plus A and a salt every time. So this is your example of your hydrogen. What is this right here? It's written oddly, but what is that? H plus, OH negative, what would that be?
Water and salt.
That would be water right there, right? H and H is going to cancel each other out. So you have an H2 and then an O, right? There you go. All right, so let's look through your notes and your homework. All right, you guys down there in the bottom, I'll bring you up, I can see your faces. Sonia, I haven't seen your face in a while. It's so good to see you. Hope your foot's doing better. Is it doing better?
Yeah, I'm out of the boot.
Oh, good. Being out of the boot is a positive thing. All right, so let's have a look here. This is from your notes and your homework. So, okay. What are our substances with a pH range of 0 to 6? Acids. And how about this one? What are the substances with a pH range of 8 to 14? Bases. That's good. All right. And what do acids form in water? They dissociate. There you go. Hydrogen and bases do. Everybody together. Hydroxide. We should all have that now, right? That's the thing you need to know. Let's see. Great. So what's the difference between a strong acid and a weak base? Did anybody have an answer for that one?
Still slightly acidic, just because the strong acid will overpower.
Sorry, strong acid and a weak acid. Yes.
My screen did some weird on like the first part.
Oh, you need to see what they were right here? Here you go. You see them now?
No, it's on the 5, 6, 7.
You're
There.
actually frozen on my end, so. Here we go. Yeah, you're not moving on. Oh, there you go. I think you just moved. Did you just move? I can't tell if you moved or not. She's so still. No, I think you're frozen right now, Senya.
See that? Close the door and go.
All right. So what's the difference between a strong acid and a weak acid? What did you guys? The pH level. Yep. What else? Do we know what else? So they're going to be more likely to break apart into their ions in water. Strong acids are going to dissociate more readily. And when they dissociate and break apart, they're going to give off more of those hydrogen ions, which is going to make the solution more able to donate them to bases, right? So what's the difference between a strong base and a weak base then? If that was our answer for acids, then what's it going to be for bases?
Yeah.
The opposite, which would be that in a strong base, they break into their ions better, which means they give off what? When bases give off? They give off hydroxide, but they accept hydrogens. They accept the protons, right? All right, so then which solution has a greater concentration of hydrogen ions? A solution with a pH of 3 or a solution with pH of 7? Well, which one? The one with the pH of 3 or the one with pH of 7?
Which one? What?
Which one has a greater concentration of hydrogen ions?
pH of 3. Yeah.
3. You guys got it. Yep. And then what is the pH of a neutral solution? We all know this. We said it. 7. Very good. And then looks like I skipped the one before it. Sorry. The products are water and salt, right? Water and salt, water and salt. So how would you define okay, which one of these is a hydrogen ion? Do you see A, B, C, D? C? That's right. That's our hydrogen ion. And how are we going to define a pH scale? D. So it's a series of numbers that indicates the concentration of hydrogen ions in a solution. Very good. And what do we get? B? Yep, neutralization, reaction between an acid and a base. Very good. And then the last one is A. So an ionic compound can form from a reaction of an acid and a base. So that's like today we're going to be making sodium chloride in our lab. And then also something else. What now? An E. Oh, I can't see their little. There we go. Hydroxide. There it is. That's the OH negative. You're right. All right. So here was your question. Let's see what you guys came up with. See if you remember it. If you turned it in, also if you didn't, maybe you've got it in front of you. So use the reaction between hydrochloric acid and then what's this one? Anybody know? Potassium hydroxide. To describe a neutralization reaction in terms of reactants, products, litmus paper, and pH. Anybody have one thing they want to share? If you have it with you, it's cool. If not, do you remember? Nobody remembers. Okay, so at the bottom here, I put our litmus paper. I'm gonna move them up so you can see it. Whoopsie. So here we go. We have blue litmus paper and red litmus paper. Red litmus paper is really big. I don't know why they call it red. And then here's our chemical equation, right? HCl plus KOH. And what are we gonna get from it? KCl and H2O. What's KCl? What kind of a compound is it? There's water. It's a salt, because here's an acid, here's a base, so it's a salt, right? Always going to get your salt in your water. This potassium chloride. We use potassium chloride. When do we use it? We used it a couple times at the beginning of the year when we were doing some crystallization stuff, and then we did it again when we lit things on fire and watched for color. That was hard. That was one of the things we lit on fire. All right, so for hydrochloric acid and potassium hydroxide, these are our products, these are our reactants, right? So you have your acid and base, and you yield a salt and water every time, every time. So then I wrote out what they were. So what's going to happen here? Our litmus paper just changed. Did you see it? It was so fun. Look at, watch my little animation. There it goes. Whee! There you are. So your litmus paper is going to change, right? If you have blue litmus paper, that's for bases. And if you put it in an acid, it's going to change color. And you have pink or red litmus paper, and it's for acids, but if you put it in a base, it's going to change color. So that litmus paper will change color with an acid or a base. Now, if you put what should happen to either of those litmus papers if you dip them in this solution that you have here at the end? the potassium chloride and water solution. They won't change, right? Because it's not acidic or basic, it's neutral at that point, right? It's neutral. So what we're gonna do today, I'm gonna show you all real quick, because I started to work on the PowerPoint and I put in some numbers. I didn't like my numbers, I really didn't. So I don't know, I had some issues with my numbers. So we're going to use everybody's numbers from today. But what we're gonna end up doing, and I wanna make sure I kind of show everybody, here's some sample numbers that are in here. Get to the one that has all of them. So what we're doing today in lab, and what you guys at home will see in the video when I get the video published, hopefully later tonight, if not first thing tomorrow day. So these are some sample numbers for what went in, and they're not right because I need to fix them. But I had a mislabeled solution, so it was a mess. Anyway, you're going to end up finding the average of these two numbers and these two numbers, because this is 2 milliliters of hydrochloric acid, and we're going to add a certain number of drops to it. And then we're going to see a chemical change occur because we're going to have an indicator in it that will change color. So we'll know that a chemical change has occurred. And so you're going to get, how do you get an average? Does anybody know how to get an average?
Median. How do we get a?
We're just going to get, well, mean, not median. So mean. How do we get a mean?
Add everything up, divide by the numbers of things are.
Exactly. So we're going to add the two numbers we have here and here and divide by 2 because we added up two things together. So if I were going to say, what's the average age of students in this class? Let's make sure everybody knows how to do an average. So let me see. Let me write them down. Let me write them down. I don't have a marker. Oh, where's my marker? I'm gonna write them on the board. How old is Ella? 13. Whoops. Okay, I'm killing my computer. Plug. So Ella is 13. I'll turn this a little. And Lily is 13, right? And Drew is 12. And how old is Jules? 10. 10. And how old is Eleanor? 10. And how old is Alec? 12. Senya, you just turned 11. Sky, Jocelyn,
Yeah,
how old are you?
I'm 12.
12. Sky, how old are you? Should she want to tell me?
12.
12. All right. Who can add them? Who's good at adding them? Go for it. 6, 13, 10, 14, 15.
105.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 105. Eleanor, you're fast. All right. How many kids do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. We got 9 on there. So we're going to do 9 into 105. We're going to get 15, 9.
Work that fast.
Well, this one's not too bad. So then what are we going to get? So what's our average age?
11.6.
About 11 and a half.
I don't like these. I try to skip these.
So we would say the average age of our class is approximately 11 and a half. Okay, that's average. That's also called a mean. You may hear the word mean. Median is different. Median is when you look at all these and see which one shows up most frequently. Say there was a 9-year-old in here, but there was also a 16-year-old. That would throw our average one way or the other. But your median is which one shows up the most. So we have 12 showing up 1, 2, 3, 4 times. So 12's that's gonna be our median, right? But our mean or our average is 11 and a half. So what we're gonna do today, what?
It's 11 2/3.
Oh, you're gonna go, oh, what, yeah.
Well, it's a
I'm
lot.
being
It's
rough.
the repeating decimal over the.
Right. I'm averaging now. I'm rounding generously. All right, so what we're gonna do today is there's gonna be like several layers of averaging, just so you know. So you're gonna get, each of your groups is gonna do a trial twice. You're gonna add NaOH, a certain number of drops, to HCl, okay? And then you're gonna count the number of drops. And you're gonna do this once, and let's say you get 10. Then you're gonna repeat it. And let's say you get 12. All right? And then you're gonna give me an average, which you guys can probably already see is gonna be 11, right? But this is when you're using 2 milliliters. you're also going to use 4 milliliters and you're going to run it again. And then you're going to give me that average. And then you're going to use NaOH and H2SO4. And you're only going to run it once with 2 mil. Okay, well, one measurement, you're going to run it twice. So you're going to get some number, and an average, some number, and an average. So you're gonna give me 3 averages. And then I'm gonna take the 4 lab teams and I'm gonna get the averages from the 4 lab teams, and that's what's gonna go into the video. Cool? What? Okay, so if we all decide, we're gonna play it by ear. We may decide that we're gonna use the group averages for our data, just because the trick with this lab is you're using a dropper, a pipette, and you're dropping, and it's really easy to like lose count, you know? So we may end up using this data for
I
everybody.
think some people will actually drop more.
Yeah.
I don't think I'm not bored.
Well, that's
I'm not
what this
agree,
is.
but some people might have not used to dropping before.
Well, that's what, so I was gonna say one more thing before I let them
I
go.
think that's so-
This is the thing about the dropper.
You put it-
If you squeeze more, you're gonna get a bigger drop. I mean, hold on a second, Lily. You're trying to get, an average size, kind of a regular size drop, but it doesn't always work that way. So what we may end up doing is using everybody's data and combining it. I'm not sure yet. I'll decide when I see how it goes in there today, but hold on a
You
second.
might want the median.
What we're gonna end up using next, what we're gonna end up using next week and from here on is we're gonna use the burettes in a particular way that takes that problem out and makes it extremely accurate. Today is just kind of introducing you to a burette, but it doesn't really, we're not using them the way they're meant to be used. So it'll make more sense when we start using them the way they're meant to be used. We won't have this problem anymore because it's really, really accurate as long as you count and you don't lose count. And you don't even have to count sometimes because it's not drops you want, it's measurements, and the measurements are extremely accurate too. All right, so I'm gonna let these ladies here go. Goodbye, ladies. It was good to see you all.
Goodbye.
Y'all be good, behave, all that good stuff.
I'm hungry.
No, go eat. All right.
I only had
later.
4 French toast sticks this morning.
Oh, you gotta send us a picture of syrup packing. I wanna see it. All right, catch y'all later. Bye. All right,
What number lab is it?
this is 24.
What do I need to put in?